Okay, so let me start by reminding you where we are in our discussion of fundamental groups. So given a space X, we want to compute the fundamental group of X. Sorry, this is being slow. And we've devised a general strategy for doing this. So if X is the geometric realization of some simplicial complex, then as we discussed last week, the fundamental group of X is, well, it's isomorphic to the fundamental group of this geometric realization, which is isomorphic to what's called the edge group, where you look at combinatorial loops rather than topological ones. And this we gave a presentation for, which we call GKT, and T is a maximal tree in this simplicial complex. So we proved all of these isomorphisms are proved except for this one, which this is what we'll call the edge group theorem. And we'll prove that later this week. And right, the point of all of these isomorphisms is that this last group, GKT, is I'll say straightforward to compute. Although it can be tedious. Especially if your simplicial complex has a lot of simplices. So what we're going to talk about today is, well, a different computational tool that does use some of this discussion. But so what it does is, if you have a space X, which is described as a union of two subspaces, A and B, then I'll explain how we can describe the fundamental group of X in terms of the fundamental group of A, the fundamental group of B, and the fundamental group of the intersection, with some mild assumptions. Okay, so right, so let me start to explain how this goes. And we're going to do everything combinatorially. So instead of spaces X, A, and B, we'll work with simplicial complexes. So let's start with K, a simplicial complex. And K1 and K2 are subcomplexes. So I guess I haven't said what this means exactly. So remember, simplicial complex, we have some vertex set, and K is a subset of the power set of this vertex set. And K is supposed to satisfy certain properties. Being a subcomplex means K1 is a subset of K, and K1 is also satisfies the properties of a simplicial complex. So this is what it means to be a subcomplex. I mean, pictorially, you know, if you sort of easy to imagine what a subcomplex is. You know, you have the subcomplex has its own vertices, which maybe are all or some of the vertices of K, and it has its own edges, and maybe it has some higher dimensional simplices as well. So here's like K1 in K. Okay, so we take two subcomplexes and we want their union to be everything. Yeah, so with K is K1 union K2. And let's fix P a vertex of the intersection. And we'll also assume that the intersection is connected. Okay, so this is going to be the setup. And we'll see some examples shortly. Or actually, maybe I'll give you a couple. So we're going to look at two examples. Maybe I'll give you those now so you have them to think about. So the first example is a complex whose realization is the wedge of two circles. And I think we've seen this example before. It looks like this. And for K1, I'm just going to take this left part of the picture, and for K2, I'll take the right part. So here's K2 and here's K1. And the vertex, so there's these vertices here, and the intersection of K1 and K2 is just this one point, P. Okay, that's the first example. There's well, okay, yeah. Let's just start with that. So the oops, sorry, I lost the vertices. Okay, just want to create some more room. Right, so the thing I want to point out now is that, so there are homomorphisms when you have a subcomplex, you get yeah, sorry, let me say it this way. So if L in K is a subcomplex, then there's a homomorphism EL P to E K P. I guess I should also say that P is the base point of K is also an L. But so the way this works is given an edge loop in L, well, L is a subcomplex of K, so it's also an edge loop in K, and that's what this homomorphism does. So I mean, like in this example, you have K1. If you take some loop based at the base point P, then that's also looping K. Okay, so that's straightforward. And in particular, in our setup, with K being the union of K1 and K2, we have a diagram. So we have, let me put the edge group of K over here, and there's a homomorphism from the edge group of K1 and the edge group of K2, And there's also homomorphisms from the edge group of the intersection into like this. And these are going to be useful enough that I'm going to give them a name. So, right, so J1 and J2 is the two inclusions, or two homomorphisms. These homomorphisms, even though it's an inclusion of complexes, the homomorphism is not necessarily injective. Right, and so the main theorem, which is Van Kampen's theorem, describes this edge group in terms of these other three groups, the edge group of K in terms of these other edge groups. So it says that the edge group of K based at P is, so I'll say it like this, is the quotient of the edge group, so of this free product of the edge group of K1 and the edge group of K2. So it's a quotient of this group by adding relations J1 epsilon is J2 epsilon for epsilon in the edge group of the intersection. Okay. So this is Van Kampen's theorem. It gives a very nice description of the edge group in terms of this free product, a quotient by a free product. Let's see how this works in some examples. So first, let's do this example from before. I think I can just copy it, but let me just, let me try to copy it. That should be quicker. Oh. Yeah, okay, that's what I want to do. So example. So the first is this one. So here we have well, here's K1 and K2. The intersection of K1 and K2 is just the point P, the base point. And right, so the edge group here is trivial. And so there's no quotient because, oh, my pages are out of order. Ugh, that's annoying. I'll fix that later, I guess. Sorry. Let me just move these around. Right. We quotient by elements in this edge group of the intersection. So if the edge group of the intersection is trivial, then there's nothing to quotient by. And so in this case, we see that the edge group of K is isomorphic to the free product of the edge group of K1 and the edge group of K2. And these edge groups, I guess we computed them last time. We computed them before, I believe. For a triangle that's not filled in, the edge group is a circle, which is what you expect because the geometric realization, the edge group is Z, which is what you expect because the geometric realization of K1 and K2 are both circles. So we get the free product of Z with itself, which is the answer that we found before. let's do another example where the geometric realization is RP2. So let me now draw a simplicial complex. Okay, so have these vertices. And okay, so this is K, and now I'm going to pick K1 and K2. So K1 is going to be this inside disk single triangle, and K2 is going to be the rest. So K2 is all of this. All right, so now let's think about what Van Kampen says in this case. So here's K2, K1 is in red. Well, the edge group of K1 is the trivial group. And well, the edge group of K2 is Z, because K2 is, so topologically what's going on, K2 is this space, which I believe we've seen before is the Mobius band. And the Mobius band is homotopy equivalent to the circle, which you proved in homework. And as a consequence, its fundamental group is the same as the fundamental group of the circle. So, okay. Right, so now the edge group of the intersection, K2, this is also Z, since the intersection of these two, of K1 and K2 is just this outer boundary here. Right, so now to understand what the edge group of K is, we need to understand, according to Van Kampen, these homomorphisms, J1 and J2. So we have right, so maybe I'll write down a generator for, so E, the edge group of the intersection, is generated by we need to pick a base point. Let's pick our base point here and call this P. So the edge group of the intersection is generated by the loop that goes 4, 5, 6, 4. That's just goes once around this circle, this yellow circle. And the edge group of K2 is generated, this group was also Z, is generated by, well, yeah, okay, so this may be a little bit less obvious, but you're computing the edge group of RP2 in homework. And for a generator, you could take I believe 4, 5, 4, 5, 1, 4. So now one needs to understand how, so we have this homomorphism J2 from the edge group of the intersection. Let me drop the base point to the edge group of K2. And we want to know what this, so 4, 5, 6, 4 maps to, well, the loop has the same name, but we need to understand how this is related to our generator. And I'll maybe leave you to check this. This is equivalent to 4, 5, 1, 4 squared. Okay, so what you make of this is that, so this is a map from Z to Z, and it's multiplication by 2. Okay, so that means that the edge group of K, so this is isomorphic to the free product of the edge group of K1 and K2. The edge group of K1 is trivial, so you just have a single generator for the edge group of K2. Let me call it A. And then there's a relation coming from, right, so remember the relation is that J1 of E is, or J2 of E for little e in the intersection. So in this case, in our case, J1 is the trivial homomorphism. So that says anything in the image of J2 is trivial. And we showed here that the square of a generator is in the image. So we have A squared is 1. And that's the only relation. And so this group is Z mod 2Z. Yeah, so this computation, I think the combinatorial approach, it's sort of straightforward to just compute everything, but then you kind of lose a little bit of intuition. So let me just explain. So we're talking about this inclusion is the inclusion, you have a Mobius band. That's K2. And a generator for its fundamental group is given by like the central circle here. And this homomorphism is induced by the inclusion of the boundary. So the boundary is this green loop. This is one loop. And well, the thing that you observe, which I think maybe you've already observed at some point, is that the homotopy class of the boundary is twice the generator of the fundamental group. I mean, if you homotope this green into the center, you go twice around. And so that's why the generator here maps to twice the generator here. Okay. Maybe let me mention one more example. Let me take this simplicial complex. With 4 vertices and 4 edges and nothing else. And let me take K1 to be this part here, including the vertices, of course. And K2 is this part here. So I just want to point out that Van Kampen does not apply because K1 intersect K2 is not connected. Okay, so I guess I didn't write that in the statement of the theorem, but that's part of the setup here. So in particular, we'll see once we prove the theorem that, well, we're going to use that the intersection is connected in order to prove it. Okay. All right. So maybe, yeah, so I want to give some intuition behind Van Kampen. We'll prove it next time. Um, so let me draw a picture. So you have K1 and K2. I'm going to draw like this, overlapping simplicial complexes, and you have the intersection here, and there's some base point here. The intersection is connected. And well, the main thing is that any edge path, let's say, well, okay, so what I'm going to explain is that there is clearly a surjection from the edge group of K1 free product, the edge group of K2 to the edge group of K. So let me explain why this is true. So to explain this, well, what we want to do is start with any edge path in K. So that's something, it wanders around all of K, and it's via edges, so that's why I'm drawing it in this sort of piecewise linear way. And well, the point is that any edge path let me write it like P U1 up to U N P in K can be decomposed into a finite concatenation of edge paths in K1 and K2. So in this picture, so we spend some time in K1 and then we spend some time in K2. I guess I really should say edge loops, and well, okay, right. So in this situation, yeah. So there's a minor sort of point here, which is, I mean, in this point, in this picture, you spend some time in K1, and then you spend some time in K2, but the part that's in K1 is not a loop in K1. But since the intersection of K1 and K2 is connected, you can always, once you reach the intersection, you can choose a path like this. And so then you can replace this original loop with a concatenation of two loops that does the red first and then the green, and then backtracks on the green and then does the remaining of the red. Of course, that backtracking, it gives you an equivalent loop in the edge group according to the relations that on edge paths. Okay, so this shows the surjectivity. You start with any edge path, you break it up into pieces, maybe using the equivalence relation as pictured with the green edge, but you break it up into pieces in K1 and K2, and then that gives you something in the image of this homomorphism. Right. I mean, the image of this homomorphism is exactly things that first do an edge in K1 and then an edge in K2 and then a looping K1 and K2 alternating. Okay. Right. And then I guess the next thing about the theorem is, so then you want to understand the kernel. And so there are some obvious elements of the kernel of this map. Namely, if well, for if I have a loop in the intersection, so it just stays inside of this intersection, I can think of it as well, epsilon can be viewed as a loop in K1 or as a loop in K2, since it's in the intersection. But clearly they're the same loop when you map into K. But epsilon 1 and epsilon 2 map to the same loop in the edge group of K. So epsilon 1, epsilon 2 inverse is in the kernel. Okay, and then the theorem says that the kernel is generated. These elements generate the kernel as a normal subgroup. Right, so you add these relations. So this is like epsilon 1 and epsilon 2. Epsilon 1 is equal to epsilon 2, or epsilon 1, epsilon 2 inverse is the identity. Okay, so that's all I want to say about the edge group theorem for now. No, about Van Kampen, I'm sorry. I'm thinking ahead. So the next thing I want to talk about is simplicial approximation and the edge group theorem. So the edge group theorem says that the fundamental group of the geometric realization of a simplicial complex is isomorphic to the edge group of that simplicial complex. And so a main tool for proving this is simplicial approximation. So let me give you a definition. So for K and L simplicial complexes, a map between their geometric realizations is called simplicial if it sends simplices to simplices and does so in a linear way. So for example, let's take, okay, this is sort of one of the simplest possible examples. Let's take K to be the simplicial complex with two vertices and one edge. Its geometric realization is the interval. So some simplicial maps, well, okay, so the identity works. The constant map, f of x, oh, so sorry, simplicial maps from K to itself. So yeah, I'm going to look at maps from so consider maps from the interval to itself. So okay, so let's just write down some maps. So there's the identity. There's f of x is 0, constant map. Let me write these all in the same way. Okay, so we have f of x is x. F of x is constant 0. F of x is constant 1/2. And then f of x is x squared. Okay, so, well, these first two, these are simplicial, which is not hard to check. But note here that a simplicial complex doesn't have to send a n-dimensional simplex to an n-dimensional simplex. So in this first example, the second example, the whole complex gets sent to a point. But that's perfectly fine since that point is simplicial. But in the second example, or in the third example, the whole complex also gets sent to a point, but that point is not a simplex. So here you map everything to this midpoint, which is not a simplex in the simplicial complex. So that this map is not simplicial, and similarly, the last map is also not simplicial. And this one, x squared, fails to be simplicial because although it sends simplices to simplices, it doesn't do so in a linear way. Okay, so right. So let me next. Right, so the reason why we are interested in simplicial maps is, well, if you're given F, a simplicial map, simplicial maps are completely combinatorial. So you get a map between vertices, let me call it G, between vertices of K and vertices of L. I mean, this is just given by restriction. F sends vertices to vertices because it's simplicial, and yeah. And conversely, well, and let me say, and G completely determines F. So let me explain why this is true. So given X in the realization of K, there exists a unique simplex sigma of k so that x is in the interior of sigma. So like an example, so if here's x, then, well, the unique simplex, let me draw a little bit more simplices here. So here x is in this unique one simplex. If instead we chose x to be inside here, then the unique simplex would be the one spanned by these three vertices. Okay, so there, x is in some, I mean, x might be contained in many simplices. Okay, you could also choose x like this. It's in this edge, and this triangle, and this, and same for yeah, all of these edges and this triangle. But it's only in the interior of one simplex. So, and I guess if you take x to be this vertex, then sigma is also this vertex. So sigma is called the carrier of x. But okay, so what that means is we can write x as a linear combination. So x is in the geometric realization, and you have to remember that the geometric realization, so all right, and I should have said the geometric realization of sigma. So here, sigma, this is inside of the geometric realization of k, which is inside of R, some Euclidean space. This is the simplex, let's say this is simplex spanned by vertices of V naught up to VD. So then, right, I mean, that means we can write x as in the following way. We could write it as a linear combination of AI VI minus V naught. I goes from 1 up to D. So I hope this is not confusing. So we have V naught, a point on the simplex can be written in this way. So you have the two, in this picture, two vectors, V1 minus V0 and V2 minus V0, and any point in here is a linear combination of those. Okay. Now, what this tells us, since f is linear on each simplex, f of x is equal to the sum of AI f of VI minus f of V naught, because f is linear on sigma. But then that means that, well, right, this is how we defined G. G is the restriction of f to the vertices. Okay, so let me just recap what we've shown here. So the claim that we started with was that this map on vertices completely determines the map F. And the explanation is, given any point, it's inside it's in the interior of a unique simplex. And so then you can write it in this form. And then the value of f is given by this expression. So f of x is determined by the value of g on the vertices, which is the value of f on the vertices. So f is determined by its value on the vertices. Right. So this is what makes simplicial maps nice to work with. They're just maps where you do something on vertices and then everything else is determined. So they're expressed by a finite amount of data. So note then that given a map G from the vertices of some simplicial complex to the vertices of another simplicial complex, then there exists a unique a simplicial map between the geometric realizations, so that f restricted to vertices of K is just G. Right. Okay. So this kind of has a very linear algebra flavor to it. You know, when a linear map between vector spaces is determined by what it does to a basis, and given any map on a basis that defines a linear map. So simplicial maps are kind of like that, but for maps between simplicial complexes or their geometric realizations. So in general, what we would like about is, well, okay, so here's what we want from simplicial maps. So given any map between simplicial complexes, let me say it this way. So given any map, we'd like a simplicial map so that f is homotopic to S. Yeah, so this is all in the context of eventually proving the edge group theorem. So I mean, the left-hand side, these are all maps of the interval into your space. And if you knew that any such map could be homotoped into, yeah, so let me draw a picture. So in the situation of the edge group theorem, we have some space. I don't know, it's something. It's triangulated. And oops. Maybe not all of these are filled in. So let me make the two squares holes. So we have this thing which has these holes in it. And well, suppose you're given a element of the fundamental group. So that means that's some loop, and it's might be completely crazy. And it doesn't have to respect anything about the simplicial structure because it's just a continuous map. It doesn't have to be injective and so on. So you're just given something like this. Now, according to the edge group theorem, this loop should correspond to some edge loop. So if we knew that this loop, shall call it f, is homotopic to a simplicial one, well, a simplicial one, you know, it only visits edges and vertices, and you know, whatever, it goes like this, and I don't know, maybe it comes back around. It looks like something like this. Right, we would like to be able to homotope any map to a simplicial one, because that's going to give us a way to go from arbitrary loops to edge loops. Right, and the key definition that's going to help us do this is what's called a simplicial approximation. So we say f from k to l. Yeah, so let this be any map. We say S, a simplicial map, S from K to L, is a simplicial approximation of F if it satisfies this property, which is going to look a little weird. So S of X is in the carrier of F of X for all X. Okay, so this condition so let me just draw a picture. So let me just do a simple sort of situation. So say we have this V is a vertex of K, and let's say under F, it maps into the interior of some triangle. So here you have F of V. Now the carrier of F of V is this full triangle. It's F of V is in the interior of this triangle. So this is a triangle in L. And right, so S is supposed to be a simplicial map, so it should map a vertex to a vertex. So being a simplicial approximation means that S of X is one of these vertices. I mean, a priori, so this is one triangle in L. Maybe there are some other triangles, or I mean, there's other vertices. We know if S is a simplicial map, V maps to a vertex. Being a simplicial approximation means that it maps to one of these vertices that are part of the carrier of F of X. So a simplicial approximation must send V to one of A, B, and C. So roughly, I think it's not so bad to think of this simplicial approximation as saying that it sends well, yeah, this, well, okay, maybe I won't say anything else. So next time we'll talk more about the Van Kampen theorem and give a proof, and continue to talk a little more about the simplicial approximation.